Okay, today we're going to talk about another application of the idea of the derivative, and that is L'Hopital's rule. L'Hopital's rule is going to help us compute limits. So this puts us back into the end of chapter 1 when we were computing limits, and L'Hopital's rule is going to give us a way to find them more easily in certain situations. So let me first talk about why L'Hopital's rule and kind of how it works. And then, of course, we'll do some examples. So let's start by supposing we have two functions. Functions f and g, and f and g are both differentiable at 0. F of 0 is equal to 0, and g of 0 is equal to 0. We want to answer this question. What is the limit as x approaches 0 of f of x divided by g of x? Okay, of course we don't have enough information to figure this out. We just have this supposed f and g, but let me just show that there's all sorts of possibilities that can occur. For instance, one possibility is we could be looking at the limit as x goes to 0 of x squared over x. And that one we know is 0, right? Because the x's would cancel, and then you'd have the limit as x goes to 0 of x. So 0 is a possibility. We could also instead be looking at the limit as x goes to 0 of, say, let's see, x squared divided by x to the 4th. That one is infinity. Or we could be looking at the limit as x goes to 0 of sine x over x, which we've done before and shown that that limit is 1. So all these different values are possible. And so the question is, how do we figure out what's going on? Well, here's the trick behind L'Hopital's rule. And this trick explains why L'Hopital's rule works. This is not what we're going to do normally when we apply L'Hopital's rule. It just explains why it works. So let's take a quick look. We're trying to look at the limit as x goes to 0, say, of f of x over g of x. Now, we assumed, right, that both f and g are 0 at 0. So this is the same as the limit as x goes to 0 of f of x minus f of 0 divided by g of x minus g at 0. Okay, nothing has been done here because f and g are both 0 at 0. Now we take another strange departure. We're going to divide the numerator and the denominator by x. Right, we're dividing the numerator and the denominator by the same value, x, and I'm writing x as x minus 0 for a certain reason, which might not be apparent, but certainly x and x minus 0 are the same thing. Now we use the limit laws and break this into, instead of the limit of a quotient, the quotient of two different limits. As so. Now we recall, by the definition of the derivative, the numerator is equal to f prime at 0, and the denominator is equal to g prime at 0. So to find the limit as x goes to 0, apparently this has something to do with finding the derivatives at 0 and comparing them. Yeah, perhaps this is surprising. Now, this is going to be fine as long as g prime isn't 0. If g prime is 0, then of course we have an undefined situation. Okay, so let me write down what L'Hopital's rule is, right? This trick helped us see how it works. Here is the trick. If f and g are both differentiable, f at some point a is 0, g at the same point a is 0, and g prime at a is not 0, then the limit as x approaches a of f of x over g of x is equal to f prime at a over g prime at a. Okay. Now recall just one caution about L'Hopital's rule. We're not taking the derivative of f divided by g. That would involve the quotient rule. That's not what we're doing here. We're simply taking the derivative at f and the derivative at g. So just remember that we're not taking the derivative of this as a function. We're taking the derivative of the numerator and the denominator separately. Okay, so let's take a look at an example using L'Hopital's rule to see how quickly this can help us find some difficult limits. Let's find the limit as t approaches 0 of e to the 2t minus 1 over t. Note that when we plug in 0 for t, the numerator becomes e to the 0 minus 1, which is 0. The denominator is 0. And so this is exactly the type of situation where we can use L'Hopital's rule. So we have to take the derivative of the numerator, which is e to the 2t times 2, and we're going to evaluate that at t equals 0. And then the denominator, the derivative is 1, and evaluate that at t equals 0, right? So just to show you how we're using L'Hopital's rule here, this is f prime of the numerator. That is g prime there for the denominator. Then when we plug these values in, we get 2 e to the 0 divided by 1. The answer is 2. So that limit is 2. And if you want, you can check on your calculator or use Wolfram Alpha and indeed take a look at a graph and confirm that yes, 2 seems like a reasonable answer. Let's do another limit. The limit as x goes to 0 of sine x over x. We know this one is 1, right? But why is it 1? Well, if we use L'Hopital's rule, this becomes cosine of x evaluated at x equals 0 divided by 1 evaluated at x equals 0, and this is 1 divided by 1, which is 1. There we go. There's that limit that we saw from before. Great. Okay. One thing to note, there's a more general form of L'Hopital's rule with the same assumptions that says the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x divided by g prime of x. This looks very similar, but it's only subtly different. The idea is then you could keep doing this. If we do L'Hopital's rule and we still get a 0 over 0, you could do it again. This iterates. And then we have the second derivative. And so on and so forth. Okay, so this is just be aware, if you do L'Hopital's rule and it doesn't give you what you want, you can do L'Hopital's rule again. So let's do that example here. So let's look at the limit as t goes to 0 of e to the t minus 1 minus t over t squared. If we use L'Hopital's rule, as I wrote above in the general form, I can say it's the limit as t goes to 0 of the derivative of the numerator, which is e to the t minus 1, divided by the denominator, which is 2t. Now if I try to evaluate this and plug in t equals 0, I again get a 0 over 0 situation. Well, I'll just again use L'Hopital's rule a second time. This becomes e to the t in the numerator and 2 in the denominator. Then when I evaluate and plug in t equals 0, I get something I can use. I get 1/2 as my answer. And sure enough, you can go check that if you like on your calculator or on Wolfram Alpha, but that is indeed the correct limit. Okay, so there's one more thing about L'Hopital's rule is that not only is it good for finding limits at specific values, it's also good for finding limits at infinity or when functions are really large. So let me write down 3 rules for using L'Hopital's rule in different situations than the ones we have here. Rule 1. We have f and g differentiable, and the limit as x approaches infinity of f of x is plus or minus infinity, and the limit as x approaches infinity of g of x is plus or minus infinity. So here we're trying to find a limit at infinity, not a limit at a finite value like 0 or a. If you have this situation where both the numerator and the denominator go to infinity, and you're trying to take a limit, then you can use this L'Hopital's rule. Here, the limit as x goes to infinity of f of x divided by g of x is the limit as x goes to infinity of f prime of x over g prime of x. So you can take derivatives and then see if you can find a limit. And this is, of course, you can iterate this just like the previous one. If you don't get something you can compute out of this first derivative, you can do it again and have f double prime over g double prime. So that's rule 1. I promised 3 rules. Rule 2. Again, we have f and g are differentiable functions, and here the limit as x approaches infinity of f of x is 0, and the limit as x approaches infinity of g of x is 0. So if they both have 0 limits at infinity, then you can also apply L'Hopital's rule. The same conclusion. The limit as x goes to infinity of f of x over g of x is the same thing as the limit as x goes to infinity of f prime over g prime. Okay. And of course we can iterate that if need be as well. And now the final promised rule 3. Here again we have f and g are differentiable functions, and here the limit as x approaches some finite value a is plus or minus infinity, and the limit as x approaches some finite value a of g of x is plus or minus infinity. Then L'Hopital's rule applies. So not only can we do this for limits at infinity, we can do it for limits at finite numbers if we're getting something like plus or minus infinity in both the numerator function and the denominator function. All right, let's do a few examples with L'Hopital's rule to see how this works. Let's take the limit as x approaches infinity of 5x plus e to the minus x divided by 7x. Okay, here is a situation where the numerator goes to infinity because e to the minus x goes to 0 and 5x goes to infinity, and the denominator, 7x, also goes to infinity. So this is our rule 1. Rule 1 applies here. Both functions go to infinity. So I should be able to find this limit by applying L'Hopital's rule and taking a derivative of the numerator and the denominator. Now, as you let x go to infinity, the e to the minus x term goes to 0. It becomes very, very small. So this is 5/7. Another example. The limit as x goes to infinity of natural log of x divided by root x. Okay. Now, we know that both of these functions go to infinity. Natural log goes to infinity as the square root function. When you put in very, very large numbers, these return large numbers. So is one of them going to infinity faster than the other one? Are they going to infinity at a similar rate? What is this limit of the ratio? Well, this is again a rule 1 situation, and then we can apply L'Hopital's rule and take the derivative of the numerator and take the derivative of the denominator. Now, we see the numerator goes to 0. Well, here we need to do some algebra, don't we? So this is the limit as x goes to infinity. This is going to be, let's see, let's write these all in fractional form. So we have x to the -1. The 1/2 in the denominator becomes a 2, and the x to the -1/2 in the denominator will become an x to the 1/2 in the numerator. And then when we gather all the powers together, this becomes 2 over square root of x, and this goes to 0 as x goes to infinity. What does that mean in terms of the original problem? That means that root x gets large much quicker than natural log. Right? Natural log takes a long time to get large, and root x swamps it and gives us a limit of 0. Okay, let's look at one more before we go to a worksheet. Let's look at the limit as x goes to infinity of 1 plus 1 over x to the x. Well, if we just tried to plug in infinity, this would give us something like 1 to the infinity. Question is, what is that really, right? That's not, I guess it could be 1, maybe, or it could be infinity, right? This thing in here is always slightly larger than 1. So it's unclear what we're going to have happen here. And this is not exactly of the right form that we need to use L'Hopital's rule. We have to get creative here. So let's start by letting y be 1 plus 1 over x to the x. And then natural log of y is x times natural log 1 plus 1 over x. Okay, and natural log of y is equal to, let's see, how do we want to write this? Let's write this as natural log of 1 plus 1 over x divided by 1 over x. Now, why did I write it like that? It seems like I'm making it more complicated, but I want this written as something of a L'Hopital rule form. Because now, when you let x go to infinity, the numerator here goes to 1, so natural log of 1 is 0. The denominator, as x goes to infinity, goes to 0. So this is 0 over 0. This is a rule 2 situation. So what is the limit as x goes to infinity of natural log 1 plus 1 over x divided by 1 over x? Well, to do this, we apply L'Hopital's rule. Take the derivative of both the numerator and the denominator. So we get 1 over 1 plus 1 over x multiplied by negative x to the negative second divided by the denominator becomes negative x to the negative second. Then we see these cancel, and then we let x become large, and this becomes 1. So this limit is 1, but that's not the original problem, right? This is 1 is natural log of y, the thing we're interested in. So that means that y is equal to e to the 1. So this limit is not 1 to the infinity. It's actually e, Euler's number. All right, go check out the worksheet and practice using L'Hopital's rule.